Welcome, learners. This video is going to introduce you to significance tests and what that's going to look like in terms of a simulation. And then we'll more formally define it, how to do it using the normal distribution like we've been doing with our confidence intervals. You can find this in section 9.1 and 9.2 in your textbook, and also topics 6.4 through 6.6 in AP Classroom. Let's get started. So suppose somebody is an 80% free throw shooter. Now that player claims they're 80%, but we suspect that person is exaggerating. So suppose they shoot 50 free throws, make 32 of them. And when we get that sample proportion, it turns out it's only 64%. Question is that enough evidence to make us be convinced that maybe it's not 80%, maybe it's a little bit less? Let's do a little simulation to find out. You can follow this along on Stapplet.com and launch the Logic of Significance Testing applet. So we suspect that 64% is a little bit low, seeing that they're claiming that they're 80%. So we're going to investigate this by doing some shots. So we're going to take 50 shots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, all the way to 50. And I've done my 50 shots. And turns out 36 of those 50 are what I got in, and that was about 72%. Is that unusually low, assuming that 80% is our actual proportion? Well, we can simulate this, and we can do a bunch of simulations. So if I add another simulation, natural sampling variability is going to make some be above 80%, some below. And if I keep doing this and add a bunch of dots, eventually we're going to get to our distribution that's going to look more and more like a normal curve, as you would expect. So I'm going to go ahead and add a few hundred, and you can see that simulation is going to look like this. So in this little simulation, if I look at 64%, and you can see that I have 321 of these simulated dots. That's a pretty small chunk that are 64% and less. I would suspect that this person's probably exaggerating and the true proportion is less than 80%. So here's one that's already done with us. We're going to use this simulation. It's got 400 sets of 50 shots. Only three of those were 80% shooter, or only three of those were less than or equal to 64%. So my conclusion in this case would be, you know what? I think the person's lying, and the likelihood of getting 64% or lower when the true proportion is 80% is pretty unlikely by random chance. So I suspect that this shooter is actually less than 80%. That's the logic we're going to be working through here. So in a significance test, we have something called a null hypothesis. The null hypothesis is kind of like the no change hypothesis. We're always going to use equal. Okay, so in this case here, I think that that person is an 80%, or that person tells me the claim that they are an 80% free throw shooter. I'm trying to test against that claim. So I'm trying to find an alternative hypothesis. And in this case, I want to go less than 80% since that sample that he took was only 64%. Now, notice that I'm using P, that's the true proportion of shots. We're trying to test against P. So we are going to always use the parameter notation in your hypotheses. The null and the alternative hypotheses are both would be HO and HA, HO and HA. And you always want to write them like this. So HO, HA, you can write HO, HA, and always write P equals for the null. Always. Don't ever put less than or greater than, just say equals. We assume that that is true. The alternative is what we're trying to prove. So it could be less than, and it could be greater than, or if it's a two-sided, it might be not equal to. So those are a one-sided versus a two-sided tests. In the free throw shot, it's a one-sided test. Let's look at an example and we'll set up some hypotheses so we can see that in action. James is a manager at the Hawaii Pineapple Company and is interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. So we have some prior data to work with. We have our mean weight. Since it's mean, we're going to use the mu parameter. A different irrigation system was installed in this field after the growing season. James wonders if this change will affect the mean weight of the pineapples grown in the field this year. We want to state some appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So we know that our parameter is a mean in this case. So when we're talking about hypotheses, First, when we set them up, we want to do Ho and Ha. So our null is the HO and our alternative is the HA. Our null is always going to be our parameter equals. So in this case here, since our parameter is a mean, we'll put mu equals. And because of our previous data here, it's going to be 31 ounces. Now, you don't need to put the unit for the hypotheses. You just put mu equals 31 because we're going to define that parameter in context of the problem later. The alternative is going to be what we're trying to show. So James wonders if this change will affect the mean. It doesn't say will be less than or greater than, it just says affect. So in this case, we're talking about not equal to, not equal to. So when we set up our alternative hypotheses, it'll look like this. Mu is not equal to 31. We always want to define our parameter of interest. So these problems will initially be telling you to do that, but when we start doing our more formal significance tests, it's not going to ask you to do that, but you're expected to define that. So our parameter in this case is the true, in this case, mean weight in ounces of the pineapples this year. So that is how to set up a hypothesis for a mean. Let's look at another problem. You are now introduced to the concept of something called a p-value. A p-value is a very important value in statistics because it basically tells us whether or not we're going to reject the original claim. So the p-value is kind of like our threshold. It's the test of a probability of getting evidence for the alternative hypothesis as strong or stronger. Sometimes it's more extreme is the word that we use than the observed evidence. And it's very important to say, assuming the null is true. We always go under the assumption the null is true. So let's talk about this basketball player here. In the dot plot, the probability of making 64% in a sample of 53 free throws is going to be, well, I only see 3 dots here that are 64% or less. And there are 400 sets of 50 shots. So there's 400 dots. So that p-value, our simulated p-value in this case is going to be, since there are 3 of them, 3 out of 400. Well, that's a pretty small number. In fact, that's actually equal to 0.0075. So what would our conclusion be with a number so low? Since that's less than 5%, I'm likely to say, you know what? I don't think this person is telling the truth. I think their free throw percentage is actually less than 80%. I'm going to reject the original claim. I'm going to reject the null hypothesis. I have evidence to prove that the alternative, that the less than 80% is true. That's the logic behind this. So let's look at this from just a template that we can use to help us decide what decisions to make. So assuming that the player, let me highlight this here, assuming that the player is an 80% free throw shooter, there is a 0.0075 probability of getting a sample proportion of shots made of 64% or less by chance alone in a sample of 50 shots. Because this probability is so small, it is unlikely to happen by random chance. Therefore, we're going to reject the null hypothesis. We have convincing evidence that the alternative hypothesis, that the true proportion is less than 80%. So our way to kind of a little conclusion template is if you have a small p-value, let's say less than 5%, then we're going to reject the null hypothesis. That means we have convincing evidence that the alternative is true. If you have a large p-value, like 5% or more, we are going to fail to reject the null hypothesis. We do not have convincing evidence that the alternative is true. And we always want to do these in context of the problem. So since there were 3 sets of shots that out of those 400 that were less than 64 or equal to 64%, we have a very small p-value. We're going to reject the claim that it's 80%. We think it's less. Now, let's talk about that 5%, because from the beginning of this class, we've said, you know what, if that probability is less than 5% from our simulations, we think that there's significant evidence that something's up, okay? Now that 5% is called your significance level, and we call it our alpha. That's our little symbol for alpha, and that's going to be what we set at the beginning of each of these problems. And that's going to vary by problem, but generally 5% is going to be our most common one. But you'll see ones that are 1% or even 10%. And it really depends on the situation and what your comfort level of maybe rejecting or not rejecting a hypothesis is. Now, we've been using 5%, but we have to always set this at the beginning. And when we're doing our conclusions, we're never going to accept, okay? So it's not correct to say accept the null hypothesis. We have to fail to reject it. Think about going to court. You're never really proved to be innocent. You're just proved to be not guilty. So it's kind of like a guilty, not guilty situation. We either reject the null hypothesis or we fail to reject, guilty or not guilty. Let's look at another example. Calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health, NIH, recommends a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test. Your hypotheses are set up for you. So you'll see that the mean is 1,300, and the alternative is the mean is less than 1,300. Why less than? Because researchers were concerned that they were getting less. So mu is the population mean daily calcium intake for teenagers. They ask a random sample of 20 teens to record their food and drink consumption for one day. The researchers then compute the calcium intake for each teen. Data analysis reveals that the sample mean, 1,198 milligrams, and the sample standard deviation, 411 milligrams. Researchers performed a significance test and obtained a p-value of 0.1405. We have a few questions to answer with that. First, explain what it would mean for the null hypothesis to be true in this setting. Then part B, state the evidence for the alternative hypothesis. Part C, interpret the p-value. And part D, what conclusion would you make at the alpha equals 0.05 level? Let's look at the first part. What would it mean for the null hypothesis to be true in this setting? Well, the null hypothesis is the mean is 1,300. So in this case here, that would say the true population mean daily calcium intake is actually 1,300 milligrams. That's what it means for the null hypothesis to be true. What's the evidence we have for the alternative hypothesis? Well, look at our sample. Our alternative is saying the mean is less than 1,300, and our sample ends up being a number less than 1,300. So that literally is your evidence. The sample mean, 1198 milligrams, is less than 1,300 milligrams. So we have something to give us a starting point. We can run a test and determine if we're going to have evidence to overturn this. Let's look at the p-value. So with the p-value, remember the definition of it is it's the test, it is the probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence, assuming the null hypothesis is true. You have to include that. So what does that look like in our template? This is what I typically write. Write this down, leave some space for the blanks. We're going to fill that in with our context. So the template we're going to use is assuming that the blank, so this is what the null is, assuming that that is true, there is a blank probability of getting a sample, depending on the parameter, mean, proportion of some value, or more or less, depending on the direction, by chance alone in a random sample of whatever your sample is. That's a lot to take in. So let's look at one thing at a time. Assuming that what's our parameter? That's right. The true mean calcium intake is 1,300 milligrams. So notice this is the null. Assuming that the null is true. Assuming that the true mean calcium intake is 1,300 milligrams. The p-value is 14.05. So there is a 0.1405 probability or 14.05% probability of getting a sample of, what was our sample? And that sample was a mean, so a sample mean of 1198 milligrams. What's our direction of our alternative? It's less than. So we're going to say or less. by chance alone in a random sample. And who are we sampling here? 20 teens. That's the interpretation. Assuming the true mean calcium intake is 1,300 milligrams, we have a 14.05% chance of getting a sample mean of 1198 milligrams or less by chance alone in a random sample of 20 teens. That is what the p-value is. What's our conclusion? Well, it's a pretty high p-value. So let's look at this conclusion template to help us. If we have a p-value that is small, so small being less than 5%, we're going to reject the null hypothesis. We do not have convincing evidence. If we have a large p-value, greater than 5%, we're going to fail to reject it. And we do not have convincing evidence in that case. Well, this is a pretty large p-value. So since the p-value is pretty large, what are we going to do here? Well, our p-value is 0.1405. It's not less than alpha. It's not less than 5%. So we're going to fail to reject the null hypothesis. That means there is not convincing evidence that the alternative is true. And of course, you want to do that in context of the problem. So the context would be that the true mean calcium intake is less than 1,300 milligrams. We just don't have enough evidence to overturn the alternative, the null. So we can't say that the true mean is less than 1,300. Here's a check your understanding. We'll conclude this video with this check your understanding here. Then we'll follow up with another video. So the manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait longer than 2 minutes to receive their food after placing an order. Based on store records from the past year, the proportion of customers who had to wait longer than 2 minutes was P equals 0.63. To reduce this proportion, the manager assigns an additional employee to help with drive-through orders. During the next month, the manager collects a random sample of 250 drive-through times and finds that P hat, the sample proportion, is equal to 144 over 250, which is 0.576. Does this provide convincing evidence that the proportion of all drive-through customers who have to wait longer than 2 minutes has been reduced? This type of question is telling you that you're going to have to do a significance test. You should pause the video and try this problem on your own. All right, pause that video, try this one on your own. All right, we're going to get going in 3, 2, 1. Let's look at the first part. So we're going to set up our ho and our ha. So our null hypothesis is P equals 0.63. That's right up here in the problem, right? Given to you right here. This was historical data. And then the alternative is we're trying to reduce this. So to reduce this proportion, reduce less than. So our alternative would be P is less than 0.63, not P hat, P, because it's a proportion and we always use the parameter. We have to define that parameter. So the parameter is the P is the true proportion of drive-through customers who wait longer than 2 minutes. That is our parameter. B, the p-value of the manager's test is 0.0385. Let's interpret this. Remember your template. Assuming that blank, there is a blank probability of getting a sample blank, a blank, or blank by chance alone in a random sample of blank. Well, what does that mean? Well, this part is the null, assuming the null is true. Null is true, assuming the null is true. So assuming the true proportion to wait longer than 2 minutes is actually 0.63. Assuming that's true. What's our p-value? 0.0385. So there is a 0.0385 probability of getting a sample. Now, what is our sample? Is it a mean or a proportion in this case? That's right, it's a proportion. It's P. What was our sample proportion? 0.576. Which direction were we going? Less than. So 0.576 or less by chance alone in a random sample. Who are we sampling here? 250 customers. Assuming the true proportion who wait longer than 2 minutes is actually 63%. There is a 0.0385 probability of getting a sample proportion of 0.576 or less by chance alone in a random sample of 250 customers. Assuming the null is true, our p-value, that number, the probability of getting that sample or more extreme by chance alone, that's what the p-value is. So what's our conclusion? Well, it's a pretty small p-value. What are we going to do here? Let's look at our little rejection template to see what we're going to do. Small p-value. Reject the null. That means we're going to have convincing evidence. What does that look like here? Since the p-value of 0.0385 is less than alpha, less than 5%, we're going to reject the null hypothesis. That means there is convincing evidence that the alternative is true. And remember, do this in context. So the alternative is that the proportion has been reduced to under 0.63. That would conclude this video. In the next video, we'll talk about more formally setting up and calculating the p-value and everything that goes along with it. Thanks for watching.